Are we going to go on the isotopes or the mixtures for your first questions?
Our first question was the mixtures.
Okay. Yeah, there was a tough one there. Was it? Okay.
Yeah.
So go ask your question. I don't want to assume.
Well, I think we had a few, so it probably covers the tough one.
Sure.
But I think just a general one for number 4, when you're asking the atomic mass and the percent composition, I think because I was looking at it both in my mix and nature's mix, and those are kind of different answers.
Yes.
Should we just put both, like how it differs between the two?
Yeah. So that's just showing stability. Okay. So you can just say, well, here's the mixture between the different isotopes, but nature tells you what it actually is, and that is telling you the stability of those isotopes. So nature is showing you if you have only one isotope present, like fluorine only has like one isotope, then that's because it's just like any other isotope is not nearly as stable as fluorine, and it'll just react at some point to where you only have the stable isotope. In some cases, there just isn't that much of a difference in stability between different isotopes, and so then you have more equal mixtures. So you can artificially say, well, I have half and half, right? So I can come here and I can say I have one of each, right? And so then you can look at your 50-50 mixture, and then you can look at the atomic mass as a split between the two masses, right? Where if you have like, okay, well now I have 2 here. Now let's just make it more. So now if we look at our weighted atomic mass, it's 1.2. So that's actually so you can tell, oh, I am skewing towards the hydrogen 1 isotope. That must be more stable. So you can kind of look at those, but if we go like to fluorine, for example, there's only one bucket, right? There is no, and so fluorine 19 is like the atomic mass is not technically 19 for other kind of reasons of how we define atomic mass, or grams per mole, but it's like 18.999999. It's 19. There's only one. So does that help answer your first question?
Definitely. Thank you.
Yeah.
And then I think number 6 and 7 were where we were a little trumped, but I think we're probably just I know we haven't gone over the lecture for tomorrow, which probably will help us.
So is that the one with silicone and like talking about the
yeah, okay. Bill.
Yeah, so if we go here, now you have an idea, right? So if we're equal, right? Let's do equal 1, 2, 3. Right? That's showing we have I could do 2, 2, and 2, but 1, 1, 1 will give me the same answer. Right. So this is showing me, and you look at the isotopes, because it's 28, 29, and 30, then it's actually hard. If I had an equal a third of each, then it would look like I wouldn't be able to tell if it were all silicon 29 or if it was an equal mix of all 3, right? Because the average atomic mass. So when you have 2, so this is a little bit harder to tell, like what's the most common isotope, just looking at the mass. But if I start putting in more of 28, now you can see that I'm actually skewing it away from both 30 and 29. So now I can say, I probably, silicon 28 is probably the more stable of the isotopes. In this case, we have it as a 60%. So you can start seeing it. And it's just a mathematical, you just multiply the percent abundance by the mass of that isotope and add all 3 of those together. And that will equal the weighted atomic mass. And I'll probably go ahead and do that as a little mini video so that we have that showing the isotope. I didn't get to that for today's lecture, but I'll tack it onto the beginning of tomorrow's lecture. And that was my goal, was that we'd be seeing it in the lab for tomorrow, so then you can kind of see that and then I could show it to you. But that's the point of that question, is showing you that it's just a weighted average is just multiplying the percent abundance as a decimal, like 0.60, multiplied by like 28, and then add that to 0.2 times 29 plus 0.2 times 30. You add those 3 up and you get 28.57621. So this is kind of getting you to explore that idea, or seeing that mathematically, but visually.
Okay, and then to check if that's correct, is that just the equation?
Yeah, well, so you could check it just by doing the math, which I just mentioned. So let's see, I don't think I can write over the top of this. So I could go back. I'll do it here. I always hate it when people will just start saying stuff. So I'm going to do it. I'll do it in the Zoom whiteboard. Recording. Oh, I can't actually since it's on my laptop. Fun fact. Okay. We'll do it here on my iPad. All right. So then if we go back to our notepad, so weighted average atomic mass is equal to, so for silicon, since we remember those numbers, we have three. I'm just going to write out instead of equation. Well, I'll write it out mathematically, and then we'll summarize. So it's the percent of silicon 28 multiplied by 28, which is the mass, plus the percent, but as a decimal. I'll show that in a sec. Of silicon 29 times 29 plus the percent of silicon 30 times 30. And so if we put that in, that's going to be, we said for 28, we made that 0.660% times 28 plus for, it was 20%, so 0.2 here.
Wait, so where's the 0.6 and 0.2 coming from?
Oh, that was in our, here. So we had 60 for.
I see, sorry.
Yeah. No, you're fine. It makes no sense if you didn't remember that. Yeah. So I'm just using the example of 3 of 1 and 2 and 1 of the other 2.
Got it. Thank you.
Yeah. No, thanks for asking the question, because the last thing I want to do is everyone just like not saying anything and me just talking and you just being completely confused. It happens more than you think as a science teacher. Okay. So so then we have this plus now we have 0. The last one is just the same, 20% times 30. And so by doing this is called a weighted average. I am weighting the 28 higher because I have more of it. And so this is really just a way, if I pull out a silicon out of like the earth, I'm not sure the naturally occurring, we can look at that in nature, but like, then it's going to either be silicon 28, 29, or 30. I don't know which one it is, but on average, it's probably going to be silicon 28 based on our numbers, right? So when we're doing calculations, we just want to have a best guess, right? Because I can't go add up all the masses of all the different silicon in my sample. I'm going to say, well, on average, it's probably going to be this mass if I have, a bunch of them, which you would. And so if you were to do this, we should, if you multiply 28 by 0.6 plus 29.2 and then do that, then you should get a number that looks very similar. So that's all that the PhET sim is doing. So this PhET sim, all it's doing is exactly, so when it gets then this 28.57261 or 621, that is just mathematically. They're not using 28, 29, 30. They're actually using a number that has like 4 decimal places. That's why you wouldn't get the exact same number, but you should get something that's 28.5 something if we were to do that. And that's what it means by checking it.
Got it. Thank you so much.
Yeah, that was probably the harder question of those. But again, that's just really having an understanding. The whole takeaway, and I'll say this, in kind of for lecture tomorrow, is that there is no, if you look at the periodic table and the weighted atomic masses, there is no like silicon with a mass of 28.57621. You're silicon 26 or 28, so you're silicon 29 or you're silicon 30, right? So, and this is a very common misconception we get all the way through chemistry, that, we don't, that is actually just giving us all the isotopes. And most atoms we can see have more than one isotope, okay? So if we look at nature's mix, so what is nature's mix? We can see, on this one, nature's mix, that, wow, it is all silicon 28, okay? You have no way of predicting that. You don't know, like, why things are more stable. So, it is under 20, so you would expect maybe 14 times 2 is 28. That makes sense. It's kind of under that, kind of like where neutron rich is more stable. So that could be a good guess, but it's really hard to tell. You just don't know. So, but that's why you have the ability to change it and kind of see. But then if you look at the average atomic mass that we find on the periodic table, it is 28.08. Like that's almost 28. representing that almost that weighted average is you're multiplying 28 by almost 100%, like 92.2. Okay, so you can think about conceptually, think about mathematically. It's trying to have you connect the two in the simulation. And like just to give an example, we're gonna do carbon-14 dating in class or in lecture tomorrow. And so you can see here that there's not even a carbon-14, that we have 98.93% carbon-12 and 1%. So like what percentage is left of, it's not even enough to consider in the simulation, but we'll talk about carbon-14 tomorrow. It is enough that we can actually use it as a way to date and measure. So that's just showing you kind of like, that low abundance isotopes can actually still be important. So anyway, other questions with this lab?
I actually had a question about number 5 in the mixture section.
Can you read number 5? Because I don't have it in front of me.
Yeah. It says, give evidence to support or dispute in nature the chance of finding one isotope of an element is the same for all elements. I'm not quite sure how to approach that.
So read it one more time. I just want to make sure.
Give evidence to support or dispute. In nature, the chance of finding one isotope of an element is the same for all elements.
Oh, that's what we just were talking about. Like, so for carbon-12, we know that's not true, right? It's not like statistically, there's 2 isotopes, it's 50-50. Like that would just be random. Isotopes in nature are based on stability. And in most cases, there's one isotope that's more stable than the rest. In some cases, like carbon, it's dramatically favoring that double. The atomic mass is double the atomic number, or to say the number of protons and neutrons are equal. Okay. But once you go up above 20, atomic number of 20, that is not true at all.
Okay.
Yeah, so it's just having you, because if that were true, then everything would just be like, the atomic mass would be like 12.5 for carbon. It would be an average of 12 and 13.
Gotcha. Thanks.
These are good questions. Others?
For question 7 on the isotope, for A, when it asked you to determine the average mass of iron, I know you just went over the equation, but when I was looking online to figure out what the equation was, it was the percent times the weighted average. Oh, actually, that doesn't make any sense.
Yeah. Sometimes online's wrong. So it's a percent times the weighted average is the percent times the mass of the individual isotope.
Yeah, that's what the individual.
Yeah. So you should, if you know the mass of each isotope and you know its percent composition or what percentage it makes up in nature, then you just do just like we did, where you multiply that percent as a decimal, so like point something, by the mass, and then you add all 3 of those together.
Okay, thank you.
Yeah.
For that one, what would it mean if you get a different answer, like iron on the periodic table is 55.845, and you get, I don't know, something that's higher or lower? What would that mean? That like it's less stable? Like, would that deal with stability? Like, why would that be the case?
You should get the same number if you're using the same numbers. And what probably is happening is you're not using the same numbers.
I haven't done it yet. I was just curious.
Yeah, no, so that's what I'm saying. And even if you look at different periodic tables, the numbers are slightly different. And so, at some point, someone had to go out and measure the percent abundance of all the elements, right? And that could continue to be done. It can be repeated if someone pays for it. So one is that they're using different number of decimal places, which you could change the answer slightly. Or in some cases, some tables are just using different numbers for their percent for each of the isotopes. So in either case, it's close enough for what we're doing. But I would not expect your numbers to match precisely with what the periodic table has, because they tend to use way more decimal places because they're trying to be as accurate as possible than the numbers that you'll be using in the sim.
Got it. That makes sense. Thank you.
Yeah. Other question.